in this video, we will implement graph neural network with GraphSage. In order to follow along, you will need to install the deep graph library, which requires the following dependencies. You will need Pydantic, PyYam, NumPy1, Touch 2.1 with the following attributes on Touch Vision and Touch Audio. Once you have installed these dependencies, you can proceed to install DGL using this pip install command. First, why graph is important, that is worth studying. For me, most data structures follow some graph pattern. For example, a social network like Facebook or Twitter can be considered as a huge graph in which users are the nodes of the graph and edges are connectivity between the users. In natural language processing, we can consider each sentence as a graph, each word as a node, and any two words are connected by an edge. In this case, we have a special graph called complete graph. In molecular data sets, each molecule can be considered as a graph in which atoms are nodes and the edges are bonds between atoms. Now going back to the video, we will study a specific graph convolution layer called GraphSage. We will build a simple GNN using GraphSage as convolution layers, and we will use our GNN to train it on a simple dataset. First, we will look at the dataset that we are using for this notebook. In this notebook, I will use the Cora dataset. The Cora dataset is the dataset of one graph of a citation network in which nodes are papers and edges are connectivity between papers. In order to load this dataset from DGL, we need to import DGL. First, we need to import DGL and Touch. We need to import DGL.data and load it from DGL. So here we already have one graph that I already checked it out, which is the graph G. On this graph, there are train marks, validation marks, and test mark, which are Boolean indices for the train, validation, and test nodes. Here, we each check these marks, and we can print out how many train nodes, validation nodes, and test nodes are there. And here are the information that we receive. So in this graph, there are 2,700 nodes. That means 2,700 papers. There are about 10,000 edges. The edge features has dimension 1,400. There are 7 classes for the nodes. We have 140 nodes for training, 500 nodes for validation, and 1,000 nodes for testing. So before we jump into doing the code, I want to have some revision on the DGL framework. The DGL update node feature based on the graph structure via 3 steps. First is a message function, which is a function on the edge. By calling this function, we send the information from a source node to a destination node. The second function is the reduce function, a function on the nodes. So this function implements the update equation for the node features. So in this function, we use the information from the message function to do the update equation. And the last function is the update O function. By calling this update O function, it does both message function and reduce function simultaneously. So these are the 3 principal steps that are required to update the node feature. In the case our, let's say our update equation involves the update of an edge features, we will use the apply edge function in order to update the edge features. Now we will look at the update equation for GraphSage. GraphSage is a convolution layer in a graph neural network which updates as follows. So the feature of the node I is updated to be a linear transformation on the concatenation of the current feature of I itself and the feature h and I that is obtained by its neighbors. So h and I here is defined to be the mean of the features of the neighbors of I. If we compare this equation with the equation for GCN, there are similarities and differences. So the equation for GCN is the feature Hi is updated to be a linear transformation of the weighted average of the neighbor node features. So in this equation, the neighbor nodes here do not include the node I itself. Hence, this equation will lose information of the node I. On the other hand, the equation for GraphSage combine the current feature of the node I with its neighbors. So I would say that GraphSage retain more information of the node I itself as compared to the equation for GCN. So now we are going to implement this update equation in DGL. So first I will import DGL.functions. So I can use the built-in function from DGL, and we want to implement Sage Convolution. We will init with in dimension and out dimension. So note that in this case, I will only need to init the linear layer, which is the linear transformation here, which take in dimension equal to twice of the given in dimension, because we have the concatenations, and out dimension is the same. Now for the forward pass, we need to take in the input graph G and the input feature nodes H. G is the input graph, H is the input feature nodes. We want to do the computation within the local scope of G. So here, well, if we are not using the built-in function from DGL, we will need to define, in fact, before this, we need to define the message function on the edge. We need to define the reduce function on the node. And then in our forward pass, we can call g.updateO, which take in this message function and reduce function as parameter. So self.message function and self.reduce function. Well, the message function is a function on the edge. In this function, we will store all the informations that are needed for this update equation in a mailbox. So what needed for this update equation is the feature H and I here. And to compute this feature H and I, we need to store all the features of the neighbors of I that are Hj, where J is neighbor of I. And for this function, there is a built-in function in DGL, which is called the function copyU, in which we can just copy the features. So we don't need this to write this function, but we can use a built-in function. Now for the reduce function, which is the implementation of this update equation, we will need to first compute the mean of the H and I, the mean of the neighbor features, which is H and I here, and then perform a linear transformation on these concatenations. For computing the mean, there is also a built-in function. So we will use a built-in function for the reduce function as well. There is no need to write these two functions. We will use the built-in function which is provided by DGL. So here we will first declare that H is the features. Now we are going to create a new features, let's say HN, that take the mean of neighbor nodes. So we will call g.updateO with the message function equal to fn copy u h m, and the reduce function here is the mean. The reduce function is the mean of this m, and we will declare the name hn for it. So in this case, the message function here will copy the h here to a new feature m, and so that this new feature m will be stored in the mailbox. The reduce function here will take the feature m in the mailbox and take its mean, and then it will create another name for the output, which is hn. Now if you call g.nData_hn, you will get the mean of all the neighbor features. So hn here equal to g.nData_hn. This is exactly hni which appear in the equation on top. So all that remains is to concatenate this with the original h and do a linear transformation. We want to concatenate on the last dimensions, say h, feature dimension, and we return self.linear h concat. Yeah, so nn is not imported yet. I should have done this block first. Right, so that's it for the Sage convolution layer. Next, we are going to build a simple model with this convolution layer. Before building the model, I want to set some hyperparameters in dimensions, which is dimension of the node feature of our dataset. So last dimensions. Hidden dimension will be a hyperparameter. Let's set it to 64. And our dimension is the number of classes in our dataset. So for our model, we have input. We pass it through Sage convolution layer 1. We apply a nonlinear activation function, which is a ReLU. We pass it through Sage convolution layer 2, and then we do classification. So here, let's try these functions. Sage convolution net. So for the initialization, we need in dimension, hidden dimension, and out dimension. Super init. So here I need to initialize. I only need to initialize the two Sage convolution. So self.convolution1 is Sage convolution from in dimension to hidden dimension, and self convolution 2 take in the hidden dimensions to the output dimensions. The forward here is quite straightforward. So G here is input graph and H here is input feature nodes. So first we will pass through the first convolutions GH, we apply ReLU, and then we pass through the second convolution. We will return H. So here let's print out our model to see how many parameters are there. In dim, hidden dim, and output dim. Let's say here we want to print out the number of parameters. So I would use some p.numl or p in map.parameters. We can print it out in million. We also maybe want to do one forward pass to see what is output of our model. So here we don't want to train, so just with touch.noGrad now equal to net. So here we need to take in the input graph, which is graph G. Input feature node will be G.nDataFit. Let's print out the shape of the output. If there is no issue, then the output should have dimension 7, which represent the number of classes. Class, and then module, there should be a colon. Module object is not callable. Net. So here this object is not callable. Well, look like we have a mistake here. We want to do concatenations, so it should be touch.cat. Alright, so here our model have about 0.18 million parameters, and the output has shape 2000 by 7. So the 7 here, the feature dimensions, which is also the number of classes. So it looks fine. So now let's train this model. For this, we will write chain loop and evaluation loop. So we need model graph, loss function, and optimizer in our chain function. First, we put the model to train mode. We will extract the feature from the graph, and we will extract the label from the graph. By the way, this is fit. I'm not sure if there's any mistake if I use double quote. To be safe here, let's just use single quote. Now we are doing forward and backward. First, let's do optimizer 0 grad. So here, logits is model which take in the graph and the features. Note that this is the prediction on the whole graph. However, we only want to have the prediction on the chain nodes. So when we compute the loss, we need to compute it on the chain nodes. So this loss is a loss function which take in logits. We apply the chain mask here to take out the chain nodes. Labels here should also the labels of chain nodes. Now we do loss dot backward and optimizer dot step. So in this chain function, I also want to return the accuracy together with the loss. So predictions is logits dot argmax. So it the position with the highest logit value. Then the accuracy will be how many chain nodes are there that are correctly predicted. So we compare prediction on the chain nodes and the label on the chain nodes. This gives us an array of Boolean values. We need to take the mean of this value to get the accuracy. So here I return both loss and accuracy. So that is a chain loop for one epoch. Now we will write evaluation loop for one epoch. Evaluate. We need the model, we need the graph, we need the loss function. There is no, we don't need to optimize in the evaluation, so we don't need the optimizers. So here, whenever we do the evaluations, we don't want to keep track of the gradient, so we will use a context manager touch.noGradient. First, we will put the model to evaluation mode. We do exactly almost the same thing as before. We extract the feature and we extract the labels. We could do forward pass to get the loss. So the logits here is a prediction on the whole graph. When we compute the loss, we want to compute it only on the validation mask. Logits and compare with the labels also on the validation mask. Now we will compute the accuracy. So prediction in terms of class label will be the argmax of the logits, and accuracy here is the number of correct predictions. So here we compare the prediction on validation mask with the label on the validation mask. There's no need this bracket. We convert this to float in order to take the mean. And we return both loss and accuracy. So now let's train this for a few epochs. We want to, let's set a manual seed. Well, let's call the model again, and models, set model loss and optimizer. So the model here is SageConv net, which take in dimension, hidden dimensions, and output dimensions. Loss and optimizers. Loss first. Loss function in this case is simply the gross entropy loss. For optimizer, we use the AWW optimizer. So we optimize the model parameters. Learning rate, let's set it to 0.01. Let's change this for 30 epochs. So for epochs in range number of epochs, we will call the chain functions on the graph G, and we take in loss function and optimizers. The training will do validations, validation loss, validation accuracy, evaluate model graph G and the loss function. We want to print out what we get. So epoch plus 1, so that we can start from the first, when the print out start from the first epoch. Let's print only up to 4 decimal places. Chain accuracy into 2 decimal places with percentage, and then validation loss and validation accuracy. All right, let's see how it works. So in the evaluation functions, okay, so here I made a typo, should be loss function. Right, so we can see here that after 30 epochs, the training has no problem. The train loss go down nicely, and after 30 epochs, we are able to get the validation accuracy of 77%. So here we are already overfitting the train data, right? Because the chain loss is going down to 0% and chain accuracy is already 100%. So that is the GNN with GraphSage as convolution layer, and we have written this GraphSage convolution layer using the DGL blueprint, that is use the message function, reduce function, and update all. So this is for the purpose of learning GraphSage and DGL. In the next section, I'm going to use the built-in function that is provided by DGL, write the exact same model, and use the same training regime in order to train the dataset. So the built-in function provided by DGL is the Sage Convolution here. It takes in the input dimensions, the output dimensions. The aggregator type here is the way that we aggregate the neighbor features. And in this case, because we take the mean of the neighbor features, so we should pass in aggregator type equal to mean. If we take in, let's say, the sum of the neighbor features, we can pass in sum. There are a few choices for aggregator type. It can be mean, sum, max, or min. You can look up at the official website to find out more about aggregator type if you like. So here, I will first need to import this SageConv from dgl.nn. So our model is the same. From the input, we pass it to Sage Convolution layer 1 to ReLU, Sage Convolution layer 2, and then use the output for classification. Class SageConv. Yeah, let's distinguish with the earlier one using capital letters. Well, this auto suggestion is too fast. So here I need in dimensions, hidden dimension, and out dimension. Super init. We have two convolution layers. The first one is Sage Convolution in dimension, hidden dimension, aggregator type. In this case, is min. And another one, take in hidden dimension, out dimension, and aggregator type is also equal to min. So that is the init method. For the forward, we do the same forward as before. First, we pass through the first convolution. We take a reloop, and then we pass through the second convolution. So our next model, let's do it, model 2, is the model which uses the built-in Sage Convolution from DGL. And let's print out how many parameters are there and compare it with the model which we write from the scratch. Model 2 dot parameters. We also print out in million parameters. And yeah, let's see. Alright, so this model has 0.184391 million parameters. If we look here, we have exactly the same number of parameters. So yeah, it matched with our model before. Now let's look at let's see whether the training match. So to do the training, we will go again the model, the loss function, and the optimizers. Model 2 here, we'll just go it again here. Loss function is the cross entropy loss. Optimizer here is the AMW optimizer with learning rate equals 0.01. Let me check here again to make sure we use the same things. Okay, same things. So now we also change the model for 30 epochs. And here I only need to replace model by model 2. And let's hit the enter button. Alright, so here after 30 epochs, the chain loss is 0.0083, validation loss is 0.73, and validation accuracy is 78%. So if you compare this to the model that we write from the scratch, the chain loss is smaller, validation loss is also smaller, not by a significant amount. Validation accuracy 78 and 77 is better by 1%. I think the difference is in the initialization of the built-in model. So yeah, that's it for the tutorial today, and we have gone through detailed step in how to write the GraphSage Convolution layer, how to use that layer to build a graph neural network and use our network to train a dataset. Thank you and see you next time.